Welcome, everyone. I'm Penny Lewis, the Executive Director of the Ecological Landscape Alliance, and I'll be the moderator for today's webinar, Climate Change and its Effects on Trees and Their Relationship to Insects. This is part of the Focus on Sustainability webinar series developed by a group of organizations known regionally for their quality ecological education. By collaborating on these webinars, we expand the reach of our regional programs across the country. In case you're not familiar with our organizations, they're largely nonprofit and volunteer groups in the United States. The groups are the Ecological Landscape Alliance, the Chesapeake Conservation Landscaping Council, Deep Roots Kansas City, and Rescape California. And now I'd like to introduce our presenter, Dr. Daniel Herms. Dr. Herms is Vice President of Research and Development at Davey Tree Expert Company. Prior to joining Davey, in January of 2018, Dr. Herms was a professor in the Department of Entomology at Ohio State University, where he served on the faculty for 21 years. His research has focused on the interactions between trees and insects, including the effects of climate change. Dr. Herms has been inducted as a Fellow of the American Association for the Advancement of Science. Welcome, Dr. Herms.
Thank you, Penny, and thank you, everybody, for taking time out of your schedule today to join the presentation. So I'm going to talk about, well, here's an outline. That Earth is warming. That's caused by greenhouse gas emissions. We're seeing signs of warming everywhere already. I'll talk about how hot it's going to get and what the impacts on trees are, and in particular interactions with insects, and kind of conclude with a little bit about what it'll take to slow warming into the future. And this story I'm going to begin with starts about 350 million years ago at the dawn of the Carboniferous period, where conditions on Earth were ideal for the formation and accumulation of fossilized plants. Carbon dioxide concentrations in the atmosphere were quite high, 1,000 parts per million, ideal for photosynthesis. The climate was warm, the continents were clustered around the equator, the Earth topography was quite flat, there was a lot of swampy areas, and the conditions were just right for the accumulation of coal and oil and gas. And as the carbon became sequestered into fossilized form over 50 million years or so, the carbon dioxide concentration in the atmosphere steadily declined as it accumulated below ground. And as CO2 declined, the Earth cooled, and eventually the glacial era begins. So fast forward to the late 1800s, and the realization developed that carbon dioxide was a greenhouse gas. These fossilized carbon were now becoming fossil fuels that were being burned as the Industrial Revolution began, and the Swedish scientist Svante Arrhenius discovered that carbon dioxide was a greenhouse gas. And in the late 1890s, he predicted that continuing to burn fossil fuels would cause global warming as CO2 accumulated in the atmosphere. In fact, he calculated that doubling atmospheric carbon dioxide would increase global temperatures about 5 degrees Celsius. And that actually has turned out to be a fairly accurate projection still to this day. So we continued really with this grand experiment to test his prediction. And since the beginning of the Industrial Revolution, we have burned about 25% of that carbon that deposited during the Carboniferous period, returning those fossilized fuels to the atmosphere as carbon dioxide. And this has led to a dramatic increase in atmospheric carbon dioxide. So CO2 in the atmosphere is now much higher than it's been in at least the last 800,000 years, and really probably the last several million years, and certainly much higher than it's ever been in human history. And So humans appeared about 300,000 years ago. Carbon dioxide has fluctuated through the ice ages from about 300 parts per million as a maximum until very recently. And we see this dramatic increase to unprecedented levels going back at least several million years to it, where it is now at 415 parts per million. And the increase is extremely rapid. And associated with this increase in carbon dioxide has been this steadily warming climate. The average temperature of the Earth's surface has increased about 2 degrees Fahrenheit since the beginning of the Industrial Revolution, and most of that warming has occurred in the last 30 years. 18 of the 19 warmest years have occurred since the year 2000, and the last 4 years have been the 4 warmest, and 2019 is going to join that crowd in being one of the top 2 to 3 warmest years. So this trend is continuing steadily. 2 degrees Fahrenheit may not seem like a lot, but consider that the temperature difference between the coldest part of the ice age and the warmest period of the interglacial maximum is about 9 degrees Fahrenheit. So 2 degrees Fahrenheit is a substantial chunk of warming, and as we'll see, the effects are already well apparent. Now, for the Earth to warm or cool, for the surface temperature to change, something must force or impinge upon the thermodynamic balance of Earth. The global energy balance has been well studied, and if more heat comes in than goes out, the Earth will warm, and vice versa. And the Earth does have a greenhouse effect. Our atmosphere provides an insulating effect, which is a good thing. That makes life possible. Without the greenhouse effect, our temperature would be that of the moon, and life wouldn't be possible on the planet. And there's various components of the greenhouse effect: water vapor, clouds, carbon dioxide. And carbon dioxide is what is changing, as is other greenhouse gas emissions, methane, nitrous oxides, and so forth. CO2 is well known to be a greenhouse gas. As I mentioned, it's been known for a long time. And as carbon dioxide concentration increases, the amount of heat, infrared radiation that it traps increases. And CO2 has been quite stable for a long, long time, and now it's rising rapidly. When I started my graduate work in the mid-1980s, CO2 was at about 335 parts per million. Now it's at about 415 parts per million. Last year, humans put more CO2 into the atmosphere than any year in the history of Earth. And Earth is absorbing more heat than it dissipates. As the CO2 goes into the atmosphere, it's very stable on these time scale of hundreds to 1,000 years. And so it's essentially permanent on the time scales that are relevant to us. And so Earth's energy is out of balance. The thermodynamic balance is such that Earth is absorbing more heat than it's dissipating, almost 1 watt per meter squared, which is quite substantial when you multiply that over the entire surface of the Earth. That's 250 trillion watts per day of excess energy coming into the global system above what is going out. And most of that heat is trapped in the oceans, which provide kind of a buffering effect on the temperature of the surface. But to put that in perspective, that's equal to about 400,000 Hiroshima scale atomic bomb detonations, every day. That much excess heat coming into the Earth's system. And as additional evidence that the thermodynamic balance is out of equilibrium, the record high temperatures dramatically exceed the record low temperatures that occur. If Earth was in equilibrium, the ratio would be about 1 to 1, which it was until very recently. But now there's far more record high temperatures than there are record low temperatures. There's lots of other evidence of warming in the ecosystem. For example, spring is coming earlier. Thoreau kept records that have been revisited, and flowering, insect emergence, and so forth is occurring earlier in the spring. The Japanese have kept records on the blooming time of cherries for more than 1,000 years. And there was a lot of kind of random variation about when spring came until very recently, and it's becoming steadily earlier and earlier. So evidence from phenology, winters are getting warmer as well. So the USDA plant hardiness zone map was updated in 2012, and it needs to be updated again. This is based on minimum winter temperatures. When I started college at Ohio State University in the late 70s, Ohio was zone 5. Now Ohio is pretty much completely zone 6, and zone 6 even extends up into central Michigan. Glaciers are receding. Glacier National Park has lost most of its glaciers. There were 150 when it was formed. Now there's 25. And here you can see, this photograph of the iconic Grinnell Glacier taken from the same perspective, showing the dramatic retreat of the ice. Arctic ice has declined dramatically over the last 30 years. And for the first time now, the Northwest Passage has opened for the first time in human history. The Northeast Passage is also open now. And you can even take a cruise through the Northwest Passage. So cruise ships started circumnavigating the Arctic north of Canada in 2016. Unprecedented. Land ice is also melting, and this is accelerating. So Greenland is losing nearly 300 billion tons of ice every year, and Antarctica more than 200 billion, which is an increase from about 50 billion in the 1990s. And so this ice that's on land is contributing to sea level rise, and sea level rise is accelerating as well, faster than most models predict. And the rate that sea level rise is increasing is accelerating due to the melting of this ice. Other signs of warming show up in the energy in storms. So the number of hurricanes hasn't necessarily increased, but the strength of hurricanes has. So the frequency of class 4 and 5 hurricanes has doubled. So have the economic losses associated with the damage from these storms. Heavy precipitation events are increasing in frequency. And so, for example, events where you have more than 2 inches of rain at a time, and you can see with each passing decade, they're more and more frequent. This has been being observed in Ohio, bringing with it increased flooding, water-saturated fields in the spring that make planting difficult for farmers. This year was particularly challenging from that regard. Tree-damaging thunderstorms are increasing. Very relevant to our business at Davie. These are some data that were compiled by Dr. Gary Johnson at the University of Minnesota from NOAA, showing that the average number of storms that severe enough to damage trees increased tenfold since the 1960s, from 30 per year to 350 per year now. Of course, fire, very much in the news. Fire frequency is increasing. The acreage burned. The fire season is longer. It begins drier. And so the intensity of fires are increasing. So there's all kinds of biological and geological evidence that is already very apparent and will continue to become more apparent. Now, the climate has always changed. It always will. For example, ice ages over the last million years or so have occurred predictably every 100,000 years. The glaciers come and the glaciers retreat. Right now, we're in an interglacial period. The glaciers retreated from the northern United States about 10,000 years ago. And these glacial cycles have been studied, among other ways, with ice cores taken from Antarctica and Greenland, where the ice is laid down like tree rings every year, in which you can study the temperature and the carbon dioxide are locked in these rings in the isotope ratio of the oxygen and in CO2 bubbles trapped in the ice. And these and other studies Earth's rotation and so forth, have found that the glacier cycles, these 100,000-year cycles, are tied directly to changes in Earth's orbit. And so Earth's orbit changes from more round to more oval on 100,000-year cycles. The Earth tilts on its axis, 40,000-year cycles, and it wobbles like a top. And all of these changes affect the amount of energy that's intercepted by Earth from the sun, solar radiation. These changes the thermal environment of Earth, and the advance and recession of the glaciers are tied directly to these changes in Earth's orbit and solar forcing. Now, the thing is, Earth should be cooling gradually right now based on the changes in the orbit and where we are. We should be slowly headed back into another ice age in the next, 20 to 30 to 50,000 years. And Earth was cooling until very recently. Earth came out of the glaciers, it warmed, and then gradually started cooling again as we're slowly headed back towards another glacier ice age until very recently. And then you see this very sharp and unprecedented rate of warming that's occurred, again, primarily in the last 30 years. Now, as the Earth warms and cools, you get natural feedback that amplify global warming. For example, as the Earth warms, this thaws the permafrost in the Arctic, and we're seeing this in Alaska and Siberia. And as the permafrost thaws, organic matter and methane that have been trapped in the ice and by the ice are released as organic matter decomposes, releases carbon dioxide, or if it's in a anaerobic environment, a wet anaerobic environment, it's released as methane, and methane's a more powerful greenhouse gas than carbon dioxide. And so you kind of get these positive feedbacks that are caused by, that reinforce the warming caused by anthropogenic sources. There's other feedbacks as well that kind of cause this vicious cycle as Earth warms. So there's the decomposition I just mentioned. Humidity increases, so the amount of water vapor in the atmosphere is tied directly to temperature, and it responds directly to temperature. And so as Earth's atmosphere has warmed, so has the amount of water vapor, and thus the greenhouse effect of humidity has intensified. And as the oceans warm, they absorb less carbon dioxide. The oceans can become saturated, and they are. It's causing them to acidify, which is causing its own problems for marine life. But as they saturate, more carbon dioxide remains in the atmosphere. And that's just fundamental physics. As a liquid warms, it holds less gas. And so, for example, as your pop or your beer warms, it off-gasses the carbon dioxide and becomes flat. And then you have melting of the ice. So all this ice in the Arctic that's melting turns a like giant white body that reflects a huge amount of radiation back to space into a dark body that absorbs far more heat. And this is causing the Arctic to warm faster than any other places on Earth, contributing to that rapid warming in Alaska and other parts of the Arctic. So you kind of get this vicious cycle that amplifies the effects of the greenhouse gas emissions. So what about other things that could be causing this warming besides greenhouse gas emissions? What about the sun? For example, this is where the energy comes from, and so it's a natural thing to look at, and it has been looked at for some time. In the late 1970s, satellites were placed into orbit to measure solar irradiance. And this graph shows a couple things. And so, for example, this yellow line here shows total solar radiation since the satellites began monitoring that. And what you see is that the radiation goes through these 10-year cycles that are related to sunspots. The changes aren't huge. They go up and down, and on average, there's been very little change, although the sun's kind of gotten slightly less radiation, and now we're kind of back up into a period where that's increasing. The blue line is increase in Earth's surface temperature, and they're scaled to the same proportional change. And what this shows is that temperature is increasingly proportionally much more than solar irradiation. And so there's no evidence of any fingerprint of solar radiation on this change in temperature. And furthermore, the pattern of warming is not consistent with solar. So the Earth's atmosphere is warming from the bottom up. The lower atmosphere is warming, the upper atmosphere is cooling. This is very consistent with a heat blanket that's trapping heat in the lower atmosphere, slowing, reducing heat radiation back into the upper atmosphere. This was predicted by climate models before it was measured. And so it's very consistent with a blanket effect and not a heat lamp effect that you would expect if the sun was the direct cause. Volcanoes have been implicated by some as the cause of CO2, but this line, the sawtooth line, shows the increase in concentration of CO2 over time. The up and down of the sawtooth is caused by the onset of fall and spring in the northern hemisphere as all those leaves drop as they are now. Photosynthesis on a global basis is declining, which is causing carbon dioxide concentration in the atmosphere to increase. In the spring, when the leaves come back, they'll draw down the CO2. That's superimposed upon this steady increase. This shows the magnitude, the blue line, of these major eruptions that have occurred since 1960, Mount Pinatubo being the last one. And what you see is there's no signature in the carbon dioxide concentration of the atmosphere of these volcanic eruptions. They have no effect on the atmospheric composition in terms of CO2. So these various alternative hypotheses have been considered by the U.S. National Academy of Sciences, among other institutions, and rejected. The Earth's orbit, as I mentioned, is having a slight cooling effect. Solar activity, the pattern's just not consistent there. The sun's not warming. The atmosphere is warming from the bottom up. Ocean vents are not the cause. The ocean is warming from the surface down. Volcanic activity, Mount Pinatubo actually had a cooling effect for a couple of years because of the sulfates that were ejected into the atmosphere, have an effect of reflecting solar radiation back to space. Air pollution does the same thing. And so global dimming caused by air pollution has a cooling effect, but this has relaxed substantially over the last 40 to 50 years because of clean air legislation primarily. So there are just no natural or other anthropogenic explanations for the warming that we're experiencing other than this accumulation of greenhouse gases in the atmosphere. And so this shows the amount of warming that's occurred in the United States, which is about average for the Earth, about 2 degrees Fahrenheit, which is equivalent to the average increase in the Earth's surface. And you can see the warming has been greater in some areas, especially northern parts of the United States, Minnesota, New England, but also in the southwest U.S. and less in other areas. Ohio's been a little bit less than average amount of warming, and some parts of the deep south have actually cooled slightly. But on average, the Earth has warmed about the U.S. has warmed about 2 degrees Fahrenheit over the last 100 years. So how much more warming can we expect as we move forward? And these projections are based on climate models, and the biggest uncertainty in these climate models is our behavior, our pattern of greenhouse gas emissions. So will we continue to burn fossil fuels at the same rate we have been? Will we reduce our fossil fuel combustion? And so there are different scenarios in these models that make assumptions about fossil fuel consumption. You have kind of low emission scenarios in which Earth was predicted to warm about another 4 to 6 degrees Fahrenheit or high emission scenarios. And I should point out that we're already committed to another 2 degrees Fahrenheit just because of the latent heat that's already trapped in the oceans that will be released slowly over time. So this thermal inertia, even if we quit burning fossil fuel right now. And so, realistically, we're probably looking at at least a 4 to 5 degree Fahrenheit increase over what we've already experienced, but it could be much higher if we continue as a business as usual. And so these projections are based on climate models, and the climate models have performed quite well. There's now been adequate time to evaluate the predictions that the climate models were made. So for example, these were models that were published in the 1990, the first IPCC assessment. The various colored lines are the different measurements of Earth's surface temperature. So NOAA, NASA, the Hadley in Europe, the Berkeley, California, and they're all showing the same pattern. These upper and lower bounds kind of show the upper and lower projections based on models that were made in 1990. And so there's less variation looking backwards because we know what happened. We know when there were volcanic eruptions and other things. But looking forward, you can see that the temperature really this dark black line is the mean of the climate models, and you can see that temperature has tracked that pretty closely, where the models have been quite good, and they've improved since then with the science, the research, and the advance in supercomputing power that has occurred. So I think we can have a pretty strong confidence that as carbon dioxide continues to increase in the atmosphere, that we're going to continue to warm. To put some perspective into these models, this graphic from the EPA kind of shows how the climate is projected to change mid-century and end of century under low and high emission scenarios, yellow being low, red being high. And what you see is, Michigan sliding down, even under a low emission scenario, down to Arkansas. Illinois under high emission scenario, sliding down into central southern Texas. So we're going to see some pretty substantial changes. They're coming. Precipitation is also affected by changing climate, very dramatic ways in many cases, and this shows models of how precipitation is projected to change, with blue being wetter and brown being drier over time. And in the United States, summer is predicted to be drier just about everywhere as we move into the later part of this century. So these changes have had and will continue to have impact on distribution of trees. So for example, trees generally will become stressed or are becoming stressed on the south edge of their distribution, but will benefit on the north. So that means, winners and losers. So this graphic, based on the U.S. Forest Service models from researchers at the Delaware, Ohio laboratory, show, how species distribution is projected to change. So green shows the distribution of spruce fir forests. And currently these, for example, in New England, upper New England, are found in Maine. But under any scenario, they're predicted to migrate out. The yellow is the maple beech birch forest. The tan is the oak hickory forest. And what you can see is the oak hickory forest is going to migrate north. They're all going to migrate north. The forest composition is predicted to change as the century progresses. And so what causes these changes? So there's various factors that affect the distribution of trees. It could relate to their success in reproduction, could be pollination, wind-pollinated trees, the conditions might not be quite right. Precipitation suppresses pollen distribution and so forth. Transition of flowers into fruits can be affected by weather and climate. Seedling survival is very sensitive to patterns of precipitation and temperature and so forth. That can be another cause. And effects on adult trees as well. So for example, birch, the distribution of birch has been predicted by models to migrate north. It's a boreal species. On the southern limits, it's experienced more stress from drought, which makes it more vulnerable and susceptible to this native insect, the bronze birch borer, which experiences big outbreaks during drought, causes tree mortality. So bronze birch borer has been predicted in modeling studies to be an agent that accelerates the northward migration of birch by knocking it out of its southern distribution. So biotic agents, another example, are fungal diseases, which have become more prevalent, for example, on white pine in New England. It's related to increase in spring precipitation and humidity. And so these affect tree performance, survival, reproduction, and other insects. So the southern pine beetle, which is a native insect in the southeast United States, where it has periodically caused outbreaks, have caused extensive mortality of southern pines. For example, loblolly pine forest in the southeast. But now southern pine beetle has expanded its distribution. It's moved into the New Jersey pine barrens. It's moved into New York. It's been detected as far north as Albany, New York. And this is related to overwintering survival. So this is some work that a colleague of mine, Matt Ayers at Dartmouth College, did to study, to model the winter hardiness of southern pine beetle and compare that with observed temperatures. And so what this shows is the orange band is where when the temperatures reach this in the winter, 90% of the insect mortality occurs. Temperatures get down to minus 21, 22 degrees Celsius, down to minus 18 degrees Celsius. In the yellow band, 50% mortality. And this shows temperature data for a couple locations in New Jersey. And what you see is the temperatures just aren't getting cold enough there to kill southern pine beetle. It's migrated north into these areas where it's impacting these ecologically sensitive areas in the pine barrens, and areas where it never used to be able to survive because it was too cold. Similar thing occurring in the western United States in the Rocky Mountain areas, and then in Canada. Mountain pine beetle outbreaks have occurred at altitudes and latitudes where it used to be too cold for mountain pine beetle survival, causing massive tree mortality in northern British Columbia, the largest insect outbreaks ever documented on Earth. Mountain pine beetle has killed, millions of acres of lodgepole pine. So the red shows the historic range of mountain pine beetle. The black shows the range of lodgepole pine. And so there were huge areas of lodgepole pine where it was too cold, where mountain pine beetle never existed before, but it has spread north into this blue area. And in 2001, in this paper by these scientists who modeled mountain pine beetle cold hardiness and integrated those with climate models, predicted that in the late 2000s, 2010, that it would get warm enough for mountain pine beetle to survive at the highest altitudes of the Rocky Mountains, reach the Rocky Mountains, migrate down into the jack pine forest where they hybridize with lodgepole pine, and then potentially migrate into the eastern pine forests. And we know that white pine and red pine, for example, are susceptible to mountain pine beetle. So their prediction came to pass in the late 2000s as they as they said that it would. Mountain pine beetle has breached the Rocky Mountains. It has spread down into Alberta, into these jack pine forests. So we'll just see how this experiment plays out. Mountain pine beetle gets up into this area, it will collide with southern pine beetle. And, you know, it will be kind of interesting in a maybe bad kind of way to see how that ecological interaction plays out when these two outbreak species, if they do ultimately collide. Now, not all insects benefit from warming. And for example, hemlock woolly adelgid is sensitive to high temperature. And Angela Meck and Kamal Gandhi, doing research at University of Georgia, you know, discovered that at low altitudes in Georgia, the hemlock trees were quite healthy. But at high altitudes, and these are dead hemlock trees, they look like deciduous trees in winter, but they're not. They're dead hemlock trees, and this is in Great Smoky National Park. But at high altitude, hemlocks are experiencing decline, where they're being killed by hemlock woolly adelgid, an invasive species that's devastating hemlocks. And what they found is at low altitudes, it's just too hot for the insect. The trees are protected from this, they're receiving thermal protection from the heat. High altitudes where it's cooler, the insects survive well, the trees are dying. They confirmed these pattern in growth chamber studies, where they found that as temperatures exceed 90 degrees, that hemlock woolly adelgid mortality, you know, approaches or exceeds or reaches 100%. So strong evidence that heat is protecting these trees. Now, trees can be part of the solution. Trees provide substantial environmental benefits, ecosystem services, as they're known. They reduce stormwater runoff. They sequester carbon dioxide. They can reduce energy consumption by providing shade. And, you know, all of these provide, you know, some response, some adaptive response to increasing temperature and increasing precipitation. And, for example, this is a study of carbon sequestration and carbon storage of the most common trees growing on the streets of the city that I live in, Worcester, Ohio. It's a small city in Northeast Ohio. And these are the most common street trees planted. Carbon sequestration, this is the amount of carbon that is pulled out of the atmosphere each year through photosynthesis. And this is carbon storage, the amount of carbon that is stored in the wood of these trees over the long term as they grow. And so in this, you know, small town, enough carbon is being stored by just the trees on the streets to offset CO2 emissions of about 200 cars, 300 cars. So, you know, that's more than the, you know, the municipal fleet of the city. And by using the iTree software developed by the U.S. Forest Service, is free software that can be used to calculate the economic value of ecosystem services, we see that things like energy conservation, stormwater remediation, air pollution removal, carbon sequestration provide $260,000 of benefits per year to the city of Worcester, just the trees on the streets, not the trees on the parks or in the woodlots or backyards. So, you know, that's pretty substantial for a population of 23,000 people. But unfortunately, deforestation is occurring in U.S. urban forests. This study shows that over a 5-year period between 2009 and 2014, urban forests in the United States shrank substantially, losing 36 million trees each year, $100 million worth of ecosystem services lost each year. So, that's not an encouraging trend. It's one that many groups are working to reverse, fortunately. Global deforestation is slowing, but it's still occurring. So also a trend line headed in the wrong direction. The deforestation has slowed, but it still exceeds reforestation. So global forests are continuing to shrink, although in the United States, forests are increasing, a trend that's been occurring as farmland, particularly in the Northeast United States, is reverting to forest. China is seeing an increase in forests, but tropical forests, in particular in the Amazon and in South Pacific areas, continue to shrink. So over the next 30 years, as CO2 continues to increase, and right now there's no sign that it's slowing, we're going to continue to see increased temperature with high level of confidence, increased storm intensity in many areas of the country. Droughts in the southeast and the west will intensify. Pest pressure as bark beetles and other things expand their ranges. Some trees are going to be stressed and others will see increased growth depending on where they're existing regarding to the edges of their distribution. Wildfires are going to increase. Worker stress will increase as the frequency of 95-degree days increases, and trees can be a big help in adaptation, can be definitely a part of the all of the above solution. And so speaking of the all of the above solution, I want to just take the last couple slides to show, what it's going to take, what it might take to slow this warming over time. And this stabilization wedge paper is a prominent paper that was published in 2004. And to kind of walk you through what this is showing, stabilization wedges, each wedge would bring down this line, and this is the line of carbon dioxide increase, fossil fuel emissions per year, amount of billion tons per year. One wedge brings the slope of that line to here, 2 wedges to here. 7 wedges brings it down to here and stabilizes CO2 concentration by 2050, where it would start to decline. So 7 wedges would stabilize emissions, resulting in a carbon dioxide concentration about 100 parts per million higher than it is now, temperature about 5 degrees warmer than it is now. If we continue the status quo, if we continue on this line that we're on, we're looking at 850 parts per million, getting close to that 1,000 before all this carbon became fossilized, 9 degrees of warming, getting the Earth into an era that it just hasn't experienced, since millions and millions of years ago. Each one of these bullet points is a wedge. So take any 7 of these or mix and match to get, a total of 7. This is kind of what we're looking at, what we are looking at. So you can see that the challenge is, pretty substantial, and the challenge is getting more difficult with each passing year. So for example, this follow-up paper published 7 years later, 8 years ago, 2011, found that from 2004 to 2011, the number of wedges has increased from 7 to 9. And so they added a couple more wedges required to stabilize. And we haven't done anything since then to address the situation. So I suspect that this number of wedges has probably increased to, 11, 12 maybe. So, just based on the evidence and the trends, the warming is going to continue. Adaptations are going to be required in the agriculture sectors, the energy sectors, sea level rise, tree planting, so forth, to respond to these changes and to hopefully adapt to them and ideally mitigate them. So with that, I'll just conclude by saying that, there's no evidence that the slope of this line is changing anytime soon. We're going to continue to see warming at the rates that have occurred since 1980. And I'll be happy to address any questions that you might have. I appreciate your attention and thank you.
Thank you, Dr. Herms. We do have very few questions. I'm sure part of it is because most of us are just overwhelmed with all of this information that you've shared with us. The first question is about forest composition changes. Are there studies ongoing that make recommendations for trees that we could be adding to our designs to assist with migration?
Yeah, so assisted migration is a strategy for adapting to climate change. Moving species that can't adapt on their own fast enough through either evolutionary processes or physiological responses to stress. And so, yeah, there is research going on looking at assisted migration. And then, various agencies, Arboreta, municipalities, so forth, are publishing lists of trees, that would be suitable over the next 30 to 50 year time frame for planting. For example, the city of Chicago has published a list of trees that they recommend for planting that will be adapted to the environment that is projected into the future lifespan of those trees. And so, coming up with those lists requires understanding the physiological traits of the trees and their environmental tolerances to create a set of trees. And then from that set, there'll be subsets that would be, adapted to particular physiographic traits of that environment, soil type, precipitation, and so forth. So it's a little complicated to come up with a grand list of trees we should plant in the future. It's going to require lists for regional and even local places.
Thank you. Is there any place online that's gathering all of this research so that you can go to a single site to then search for your state or region or locale?
There are places online. So the IPCC, the Intergovernmental Panel on Climate Change, and their reports, the U.S. Climate Change Research Program publishes a report that summarizes these impacts. The last report was released by the U.S. government, I believe last year on Black Friday, the day after Thanksgiving. So you can go to that website and review those reports and those impacts. So they are out there. It takes a little bit of poking around. The EPA at one time had a lot of great information on their website. Most of that information isn't there anymore, but some various institutions or agencies have captured that website. So, for example, the city of Chicago, I believe, has a website that mirrors the EPA climate change website, where you can go and review that information now. They captured that before it was taken down and removed. So that, yeah, there is information out there, but unfortunately it requires, a little bit of poking around. Maybe it's not unfortunate, but it does require some poking around, but it is out there.
All right, that's good to know. What about insect and tree phrenology in relation to climate change? What will happen with the timing swings and the ecosystem as a whole?
Yeah, so that's a really good question. I want to just also back up just one moment. A great site for finding climate change information is called Real Climate, a website called Real Climate. So it's a website that's maintained by climate scientists. They do it kind of on their own time. And it's kind of a blog format, but it's very well indexed. So say you want to find out something about climate change in trees or climate change in glaciers, you can search that, and it's links to the peer-reviewed research with lay people commentary on peer-reviewed research. It's an excellent website. I've been operating it for, 20 years or close to it. So there's a huge amount of information available in it, and directly linked to the underlying research in a very accessible way. I believe that website is realclimate.org, but if you search for Real Climate, you can find that. Climate science by climate scientists. As far as plant and insect phenology and phenological synchrony, that's a really interesting question. So if insect herbivores or pollinators respond to climate change in a way that's different than their host plants, you can get phenological asynchrony, where the pollinator is not present at the time the plants are flowering, or the herbivore is feeding at a time when the leaves are not ideally suited to that herbivore. So that can create ecological problems for the insect. And what I found, and this is something that I studied pretty extensively, is that insects and trees are generally changing responding to temperature in the same way. And in fact, the variation of weather is much more dramatic than the variation in the climate. So, year to year phenology can change, by a month in a warm spring versus a cool spring. And so the insects are quite adapted. The herbivores are quite adapted to staying in synchrony with their host plants. So at least in the relative short term, I don't think it's going to be a big issue for herbivores. There's been a little bit more evidence that pollinators can be impacted more severely, and then especially where they've really seen evidence for phenological asynchrony is with bird migrations. So migratory birds on their overwintering grounds are responding to day length. They don't really know what's going on in the north in terms of climate, and they get up here and they find if they get up here too early, the trees haven't leafed out, the insects that they feed on aren't available. If they get up here too late, their food source might not be ideal. This has been documented for some Arctic species of geese that arrive too late, and the grasses have matured too much, and they're not as nutritional for their offspring. So this phenological asynchrony is a real significant thing for bird migration, for example.
All right, thank you for that. Is there any research about whether ancient species will be more likely to survive?
Ancient species?
Tree species.
Oh, I'm sorry. Can you repeat the question, please?
Will ancient tree species be more likely to survive? Is there any research on that?
Ancient tree species. So like long-lived trees, like redwood trees, bristlecone pine trees, that kind of ancient, or trees that, have been existed in the fossil record for a long period of time, like
either or both.
Ginkgo, for example. Yeah. That's a good question. I don't know if I've seen research that addresses it from that perspective. Redwood trees live for a long time, but their environmental tolerance is pretty narrow. So they're restricted to a pretty specific habitat along, the California, Northern California coastal area, and they're highly dependent on humidity and fog, getting moisture from the fog. And, as that changes, there's some speculation that that's going to stress, those trees. So they're, as their environment's been stable for a long time, as that changes, that could imperil trees just like, redwood that have survived, lots of, kind of different changes over, their lifetime of several thousand years. Same with bristlecone pines, as they're restricted to very specific narrow environmental conditions, and as those change, they'll be threatened as well. So I think trees that are more adaptable, more plastic to things like variable moisture, variable temperature may have a better chance, but I don't know if that really has been evaluated in a systematic way. Maybe it has, and I'm just not familiar with that work, but a very interesting question.
Okay, thank you. What impact does burning wood for heat have on adding CO2 to the atmosphere?
Yeah, so burning wood, you need to they make a distinction between ecological carbon and fossilized carbon. So burning wood kind of falls into a category considered as biofuels. And that is considered to be recycling carbon dioxide that's already, in the atmosphere. So CO2 removed by photosynthesis, stored in those trees. The trees are cut down, that burned, it releases that CO2. It's reabsorbed by the regenerating vegetation. And so that's considered to have no real impact on atmospheric CO2 compared to the burning of geological carbon, in which that was sequestered by photosynthesis that occurred, 300 million years ago and been stored in the earth all that time and now being released. So, biofuels are considered to be an alternative to fossil fuels that would have less impact on atmospheric CO2.
All right. And one last question. What is Davy Tree doing to lessen the impact of climate change?
So Davy Tree is heavily engaged in urban forest management, consulting, tree planting. Davy Tree collaborates with the Forest Service to develop and support the iTree software platform that's used that I talked about earlier for calculating ecosystem services. It's used by hundreds of millions of users in more than 100 countries, around the world. We're involved in tree preservation, tree planting, and so we are also have a what we call a sustainability initiative, which on our website you can see what we're doing. We're looking at ways to reduce our to increase the efficiency of our vehicles. We have a large fleet, so we're transitioning away from 2-cycle engines to battery-powered engines. We're involved in wetland restorations, water management, so forth. So we kind of have a diverse suite of initiatives that I think bear positively on the climate.
Excellent. Well, thank you so much for sharing all of this necessary but alarming information. It certainly has given us a lot of information to think about and reflect on, and I appreciate you sharing your research with all of us.
You're very welcome, and thank you and everybody else for taking time out today.